All right, hello everyone. Welcome to AISC's live webinar, Welding Special Applications, presented today by Dr. Dwayne K. Miller of the Lincoln Electric Company. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. And with that, I want to introduce today's speaker, Dr. Dwayne K. Miller of the Lincoln Electric Company. Dwayne is a recognized authority on the design of welding connections. He is in demand as a speaker on the subject all over the world. Dr. Miller frequently publishes in the industry press and on 3 occasions has been awarded the coveted Silver Quill Award of the American Welding Society. In 2001, he received the AISC T.R. Higgins Lectureship Award, and in 2005, AISC awarded him with a Lifetime Achievement Award. He has authored and co-authored chapters of many texts, including AISC Design Guide 21 on welding and Mark's Handbook of Engineering 10th edition. An AWS member since he was 19, Dr. Miller serves as the chair of the AWS D1 Structural Welding Code Committee and chair of the Seismic Welding Subcommittee. He is a former chair of the AASHTO AWS D1.5 Bridge Welding Code Committee and a member of the AISC Specification Committee. And with that, I'll turn it over to you, Dwayne.
Thank you, Brent, and for all who are joining us from the webinar. We're coming from sunny Southern California, actually in San Diego, and enjoying the nice weather out here. We have a live audience who's going to be participating with us today, and I hope you find this to be beneficial. Perhaps some background as to how this particular lecture came about would be helpful to you. When Design Guide 21 was contemplated, a series of advisors and peer reviewers was established, and they gave feedback as to what content should be incorporated into this design guide. Some of that feedback came from the AISC Solution Center. And the issues were the topics of frequently asked questions that hadn't been originally included in the draft, the outline of Design Guide 21. With no logical place necessarily to put all of the content of these questions, Chapter 12 was created that would address these miscellaneous issues that in and of themselves may not constitute major details, but were frequently asked questions, perplexing issues, and that's the coverage that we're going to be talking about today. Now, when you open Design Guide 21 and go to Chapter 12, you'll find 10 different topics addressed, and I hope to get through all 10 in this webinar. Those list of topics included extending anchor rod, welding anchor rod to base plates, welding on coated steels, welded under on heavy sections, welding under high restraint, welding HSS, welding AESS, welding on existing structures, field welding, and finally heat shrinking. So those are the 10 topics we're going to take on today as part of this webinar, starting with the issue of extending anchor rod. Now, you all know what the situation involves here. The anchor rod's been placed. You deliver the steel to the job site, put the columns in place, and you find out that the anchor rod has been set into the concrete too deep. So you have the situation wherein you can either not get adequate engagement of the threads on the nut, or in fact, you may have the situation where the rod is actually below the plane of the base plate and you can't even get a thread started. Now, it's very tempting to go out and grab your welding machine and try to weld these anchor rods to the base plate or weld on extensions to the base plate, to the anchor rod to address the issue. And that's the topic that we're going to take on right now. Now, if you do want to extend the anchor rod, the first item on our list that should be investigated is that of a mechanical option. I need to tell you, it's a little hard for a welding guy to start a seminar by saying you ought to look at bolted alternatives, but in fact, I think that's a responsible starting point. because we're going to find out that there are some metallurgical issues associated with the grades of steel used for anchor rod that may make welding problematic. Now, the mechanical options would include things like coupler nuts, and it may be undercutting the base plate and milling a cavity so you can get a nut in. A host of other mechanical options may be viable. Now, having investigated mechanical options, maybe indeed you find out that the welded option is one you want to pursue. And if we do that, the first thing we need to do is investigate weldability. Now, weldability is a term that we might use, but if I pressed you for a definition, you might come up short as to understanding exactly what we mean by the term weldability. The American Welding Society has a committee that writes a document called A3.0. And before I read this definition, I'll tell you I don't particularly care for this definition of weldability. Nevertheless, this definition reads as follows: the capacity of a material to be welded under the imposed fabrication conditions into a specific, suitably designed structure and to perform satisfactorily in the intended service. Now, I'd like to suggest that we usually don't add a fitness for service component into the use of the term weldability. And yet this official definition from AWS does make fitness for service part of this definition. I prefer the definition that comes from ASTM. And ASTM defines weldability as follows: a term that usually refers to the relative ease with which a welding material, a metal can be welded using conventional practice. Now, with that definition in mind, let's go on and evaluate what constitutes weldability. Now, weldability is driven by the chemical composition of the material. Carbon is a critical ingredient in determining weldability. The effect of carbon is compounded by the effects of alloys that are present in the material. Now, weldability is directly related to the term hardenability, and hardenability is a term that the metallurgist uses when defining heat treatment of a steel. And steels with high levels of hardenability are able to achieve high hardnesses very easily. And welding, we really don't want the steels to get to high hardenability. We prefer steels with lower hardenability. We prefer low carbon steels, low alloy steels for good weldability. So if you will, weldability and hardenability are inversely related. Now, welding engineers are also concerned with something we would call hot cracking. We're pretty creative in our terms. We have hot cracks and we have cold cracks. Hot cracks occur when the steel is cooling for the first time. Cold cracks occur after the steel gets to below, let's say, around 200 degrees Fahrenheit. Hot cracks and cold cracks. Hot cracks have to do with low melting point constituents in the steel, and two of the key constituents are sulfur and phosphorus. And so that's why we like to hold these alloys to maximum levels to make sure we don't get too much sulfur or phosphorus in our steel. Now, when I look at various anchor rod specifications, I find several things that are disturbing to me as a welding engineer. Many of these anchor rod grades have high levels of carbon. They have high levels of alloy. Some grades have undefined levels of carbon and alloy. And then finally, we have some heat-treated steels that go into making anchor rod, and heat-treated steels require even additional controls on welding. Now, there are a variety of grades of materials that could be used for making anchor rod. In Design Guide 21, and we have a copy of that at present here in San Diego, if you go to page number 63, you'll see that the topic of welding on different grades is addressed. And so you have discussion about 307, A325, A354, and other grades of material that could be used for anchor rod. Now, for today's discussion, I'm going to use F1554, which is the preferred grade for using or making anchor rods today. When you look at 1554, you'll find that there are 3 different grades of anchor listed, grade 36, grade 55, and grade 105. Now, grade 36 has a name that kind of implies it would be like A36. And indeed, if you look at the chemistry in 1554 grade 36, it's very much like A36 steel. And you, of course, know A36 is a highly weldable material, and so you would tend to have a lot of confidence when you looked at grade 36. However, there's a footnote, and the footnote says that for rod diameters up to 3/4 inch, the manganese content is, quote, optional with the manufacturer, but shall be compatible with weldable steel. Now remember, when we said weldability, we did not define that in terms of whether you could or could not weld the material. We decided it had to do with the relative ease with which you welded the material. Now, this definition in the footnote talks about weldable steel. It doesn't talk about how easy it is to weld it. And frankly, I'm not sure what it means that the manganese content shall be compatible with weldable steel. Now, as I pursued this issue with several people who produced rod or who were on the ASTM committee, frankly, some confusion emerged. And more than one supplier told me, well, this discussion about grade 36 is a bit academic because we don't make 36 anymore. If we get an order for grade 36, we substitute grade 55. Now, you can understand the logic. 55 is greater than 36, and when you're looking at a mechanical system, mechanical fastener that's subject to tension, getting a little bit more for your money doesn't sound like any big deal. But now we're not just talking about strength in a mechanical connection, we're talking about welding on this material. So now to understand what grade 55 is, the material that could be substituted for 36, we have to go and see the requirements for 55. Now it turns out 55 and 105 are lumped together when it comes to chemistry. And there are only controls on sulfur and phosphorus, meaning there are no controls on carbon and alloy. A grade 55 can be ordered to the optional supplement S1. And when you order rod to 55 supplement S1, limits are imposed on carbon, manganese, silicon, phosphorus, and sulfur. Additionally, there are 2 carbon equivalency equations that help limit the hardenability when you have welding involved. And again, that would be imposed only when you order to supplement S1. Well, let's continue and examine then grade 36 from a welding point of view. Now, the chemistry would imply it should be readily weldable, but there is confusion as to whether or not appropriately grade 55 can be substituted for 36. 36 has some chemistry controls that 55 doesn't necessarily meet. And the specification for 55 specifically says, quote, weldability is only assured if grade 55 is ordered in accordance with supplement S1. So we have grade 55 that might be substituted for 36, but 55 has weldability assured only when I order it to S1. The conclusion I come to is I'm going to need to investigate on a case-by-case basis the weldability if I have 1554 grade 36. Now, that doesn't mean it's always going to be bad. You randomly may have material that was low enough in carbon, low enough in alloy that makes a good weldable material. But you're going to have to investigate because I don't think you can assume it's guaranteed. Now, when we go to grade 36, we're essentially in the same boat as when we go to grade 55, we're in the same boat as 36 because we might have that substitution. We have no limits on chemistry. We have this note that says it's not weldable, or it's not insured to be weldable, rather, when we order it other than with supplement S1. I come to the conclusion that, once again, investigation on a case-by-case basis is required. Now, grade 55, that's ordered in accordance to supplement S1, well, there I should have pretty good confidence that my weldability is going to be fine.
Dwayne, if I can interrupt real quick, we do have a question. The question is this: how can material that did not have the S1 specification at purchase be checked if this is met?
Oh, that's an excellent question. To comply with supplement S1 are chemical requirements, and the rod could be analyzed by a materials lab, get your chemistry, get your alloys, and you would get the chemistry. You could see if it does or doesn't comply with those limits of the specification. And then there are the carbon equivalency equations. They're listed in the ASTM specification. You could make that calculation. And by making those checks, you could find out if that material that was not ordered in conformance with the supplement S1 actually, in fact, did comply with supplement S1 requirements.
Does ASTM note it as supplement S1?
The question is, does ASTM note it as supplement S1? If you order it to S1, that should be on the mill test report that you complied with S1. You should be getting the chemistry and the calculated carbon equivalency value.
ASTM has a spec S1 for that.
Yes, sir. I'm supposed to repeat the question for the people of the webinar. ASTM does have this. After you read the spec for 1554, the supplemental test at the rear of the specification will be listed, and S1 is one of those that's listed right there. Okay, so let's go back. Our grade 55, if we order it in accordance to S1, we should have good weldability. Now, I want to be very practical in this seminar. If you anticipate that the anchor rod's going to be set too deep into the concrete, then you could order the anchor rod to 1554 and order it to supplement S1. Or maybe you could tell the contractor who's setting the anchor rod in the concrete, don't set the anchor rod too deep into the concrete. Now, see, the problem is we really learn about this, we think about this after the fact, right? So chances are you're going to be not ordering it to supplement S1, but you're going to be using the material that happens to be in the field.
Before we move on, we have a couple more questions, Dwayne. Can on-site positive material identification tell one the carbon content?
The on-site is, I suspect, problematic in terms of evaluating the carbon of an anchor that's already in concrete. I would suggest you're probably going to be taking similar material or parts off of that anchor and having it evaluated in a lab, as opposed to in situ testing in the field. Now, there may be some development in materials testing I'm not aware of that would be better to do that, but I think that's going to be a laboratory test.
Okay, and then two more questions. How do you verify grade 55 during an inspection in the field? And the other question is, how does A307 compare with ASTM 1554?
All right, we have a lot of questions. I like the interaction. Identification in the field, I got to tell you, I'm not sure if that's rolled onto the rod or not, and I can't answer that particular question. As to the 307, I would encourage you to get Design Guide 21 and read about 307. I've used 1554 to illustrate the principles. Those are all discussed in the Design Guide as well, and so I'd encourage you to get those details from that. Now we have another question here. Yes, sir.
Just a clarification that really part of the primary way to classify your anchor rods is really the MTRs in the field. That gives you the information, but as far as markings, it's very consistent.
As far as markings, what was that? Okay. The comment was the most, from one of the guests, the comment was the best way to verify what you have in the field would be from the material test reports and not rely upon any markings on the rod. And I'm accepting that as accurate. That's not my field. Well, now, folks, continuing on, we just looked at grade 55 with supplement S1. I'd like to go to 105. Of course, this is a 105 KSI yield strength rod. We have essentially no chemistry control for the material. We have a very high strength material, and I can almost guarantee weldability is going to be a challenge if you have 1554 grade 105. Now, we've only gone through 2 steps. We started by investigating mechanical options. We've now looked into weldability. The investigation of weldability may take you back to looking at your mechanical options again. But assuming we went through the weldability gate and we came out all right, the next issue is to use the appropriate detail. Now, the illustration is showing the too short anchor. And above that, we have a washer, a donut that's been cut out of a good grade of structural steel. We're not using hardened washers for our mechanical systems. We're using a good weldable steel, a fairly heavy thickness of steel, where we've drilled the ID to match up with the OD of the anchor. And we slip that donut over the rod. Now, you'll see how that functions in just a moment. We bring in the extension. Now, the extension should be selected from good weldable materials so that we don't have any problems with the extension. We take the extension and grind it to a chisel point, not a pencil point, but to a chisel point, and then bring that into an alignment. Now, at this point in time, I think you can start to see the role that that washer or that donut's going to have. It's going to act as a support for the liquid weld metal. It acts as a bit of a starting tab and a bit of a runoff tab. And a bevel groove weld in the horizontal position is hard to make. That acts as a shelf to support the liquid metal a bit. And so then we go in to start the welding. We weld from one side. We could be alternating sides. I'm not going to complicate the discussion with talking about welding on either side. Let's assume we get one side welded up. We go to the opposite side, gouge the root. This is making sure I get complete fusion across the full cross-section of the rod. Weld up the second side, and now it's time to start cutting off auxiliary pieces of steel and then grinding that flush so I get a good sound extension and I don't have any weld discontinuities and I have a smooth surface. Well, that's how I can weld an extension in place. Of course, it's really tempting for somebody to look over in the corner and see their welding machine, and particularly for these anchors that are too short, they want to make a plug weld. Now, we'd like to discourage that. Number one, we don't have design capacity values for plug welds in tension. We normally look at those as in shear. There would be a tremendous influence of the base metal composition on the weld metal composition, and getting a good sound weld under those conditions would be very problematic. Of course, we had the other situation where perhaps you couldn't get full engagement of the nut in place. Once again, it's very tempting for somebody to want to get their welding machine and put a little plug of the anchor to the nut. Now, again, in the design guide, we have a segment on welding on various nuts. Nuts are usually not good materials to be welding on, and this detail would be somewhat problematic as well. Now, having made this presentation a few times, a frequently asked question is about the other end of the rod and welding on nuts. You should know that L rods and J rods are not the preferred approach, and rather we want straight rods with a nut on the end to keep that nut from spinning off. Oftentimes people will put in a tack weld to keep it from loosening. I see nothing wrong with this detail, providing that the tack weld is on the outboard side of the nut. I don't think you want to be welding on the inboard side. That is the side of the nut that's going to go next to the continuation of the rod. If you had a problem with that tack weld, I could envision some situations where the rod could crack. But if it's on the outboard side, I can't see that that would be a particular problem because all the forces would be applied on the opposite side of the nut. Well, we're down through one topic now, and that was extending anchor rod. And now I'd like to switch to the opposite situation, And that's when people want to weld anchor rod directly to base plate, and this is when we have just the opposite problem, that is the rods are not set in the concrete deep enough. Now, of course, you need to make a little investigation to make sure you have enough engagement to even get the strength out of the anchors that you're looking for. And here we start the list the same way we did before, and that is investigate mechanical options. Now, in this particular case, we usually have mechanical options that we can utilize. We can put a stack of washers in place. We can make a pipe washer, if you will, if it doesn't make sense to have a big stack of washers for the connection. But if you don't want to do that and you want to go into welding, well, once again, we start the list with investigate weldability. And we're going to do that the same way as we did before. Now, having investigated weldability, we need to use the right detail. This is typically not the right detail. Of necessity, there's a clearance between the diameter of the rod and the diameter of the hole. There will be a gap at this location. That gap is going to make it problematic of getting a good weld. Predicting the weld throat with gaps is a little bit more of a challenge. Rather, we'd like to suggest a detail that looks like this. Now, once again, we've cut a donut out of a good, high-quality steel that's easily welded. We've made the ID precisely the same as the anchor rod, so we have a good, tight fit of that donut to the anchor, and now we can put a weld around that location without problem. Now, there's no need to weld the donut down to the base plate. There might be some temptation to do so, but we're just going to be transferring some restricted loads through that connection, and we don't really need to tie all those components together. Well, having gotten through the anchor rod, I think we have a question on anchor rod.
Yeah, before we move on, the question was, what if the welded area of the extension is where the nut needs to end up?
I think I understand. So now we have an extension, and we have a threaded part of the extension, and maybe the welds in the area of the threads. I would encourage you to use some of these techniques we just went through, a stack of washers to get you out of that region, maybe this pipe washer. Those are a few details that I think some planning can avoid. I think I'd discourage the idea of trying to go back in and tapping threads through that region. I think that's an unnecessary complication that can be worked out with other details.
And then as far as washers, is there an acceptable limit of washers that can be used on a rod?
Wow, you're asking a welding guy a bolting question. And I won't pretend to know the answer to that one. I think you're going to have to probably look at that bolting design guide to get answers from that. So I'm going to dodge that one today. All right, sorry, I can't answer that. The next issue we're going to take on is welding on coated steels. Now, when I say coated steels, there are at least two common applications: galvanized steels and painted steels. And before we go into any more detail on it, let's look at what our specification already says. Now, if you look at the banner at the top, this is right out of the 13th edition, the 2005 spec, the Joint ASD-LRFD specification. When I look up the topic of shop painting, I read the following: unless otherwise specified in design documents, surfaces within 2 inches of any field weld shall be free of materials that would prevent proper welding or produce objectionable fumes. Now, if I go to section M4, I read this: shop paint on surfaces adjacent to weld shall be, to joints to be field welded, shall be wire brushed if necessary to assure weld quality. Let's see what AWS D1.1 says on this particular issue, and that topic is taken up in section 5. 515 reads as follows: surfaces to be welded and surfaces adjacent to a weld shall be free from loose or thick scale, slag, rust, moisture, grease, and other foreign material that would prevent proper welding or produce objectionable fumes. Now, within these provisions, we see a pattern. And the pattern is there's ongoing concern about fumes. There's concern about inhibiting proper welding. The kinds of materials that could be on the surface are fairly broadly defined. And I think this fourth bullet is pretty important. These standards are providing us with an outcome-based requirement. Now, most of our specifications and provisions deal with input requirements. We say that the steels can be of these grades. The filler metals can be of certain grades. What you don't find here is paint of a certain mill coverage or galvanized of a certain mill coverage can be welded on without concern. You don't see a requirement that says if it exceeds this level, you have a problem, you got to remove it. Rather, what we're looking at is outcome-based criteria which says if the weld quality is affected, you can't do it. Now, this practically means you make a weld and you inspect it and see if it's okay. And if it's not okay, you're going to have to do something different. And if it's okay, you go ahead with it. That's what I mean by outcome-based criteria. Now, there is this ongoing discussion about safety. And in Design Guide 21, there's a brief chapter 15 on weld safety. The most important thing that's contained in that chapter is a reference to Z49.1. Now, that's the ANSI standard on safety in welding and cutting and allied practices. And you can obtain a free copy of Z49.1 by going to the AWS website, aws.org, and you can download that to your hard drive. You can print out a copy if you wish, or you can purchase that document from the American Welding Society. And it has discussion A to Z of welding safety-related issues. So if you have any responsibility for welder safety, you really need to get a copy of Z49.1, read it, and follow it. Now, also at the AWS website, you'll find a listing of some 30-plus fact sheets. Now, these are 1, 2, 3-page documents that address a single topic, and it's an excellent source of input for your safety meetings for the contractors who are oftentimes looking for things to constitute those meetings. These are consensus-based documents that are produced by the AWS Safety and Health Committee and a good source of information. Now, for example, fact sheet number 1 addresses the issue of welding fumes and gases. And the next fact sheet that you see here happens to be fact sheet 25, and fact sheet 25 deals with the topic of metal fume fever. Now, if you read with me, you'll see that metal fume fever is the name of an illness that is caused primarily by exposure to zinc oxide fumes in the workplace. The main cause of this exposure is usually breathing fumes from welding, cutting, or brazing on galvanized material. The point here is if we're welding on coated materials, if you're welding on galvanized materials, here are some sources of information to address the welding fume side of the discussion. Now, the American Welding Society, fact sheet 21, here's the outline of the material covered in that document and gives you some good, helpful information. And, of course, this is the information I just read, but perhaps in a format that's easier for you to digest. Practical advice is given. Keep your head out of the fumes. Don't breathe the fumes. Use enough ventilation. Exhaust the arc to keep fumes and gases in your breathing zone and in the general area below any limits. And then also gets into TLVs, material safety data sheets, and those kinds of issues. Now, I'd like to switch gears now and go back to the issue of weld quality, but I guess before I do that, we have another question.
Yeah, one question that came in is, what are some possible solutions to inspecting welds once they've been painted over?
Oh, boy. Okay. The question is, how do we address the issue of welds after they've been painted over? Now, politely want to say that's really not what we're talking about here. We're talking about painted surfaces and welding on those painted surfaces. D1.1 will tell you you need to inspect the welds, and I think you'd find the implication there, if not a specific statement, that you're going to inspect them before it's painted over. You really should be inspecting it before it's painted. I would expect that heavy paint could mask discontinuities. In fact, I've seen a couple of projects where we had products that were actually dipped and had a very heavy layer of paint over the welds that made inspection of it impossible. So there may be some metal removal paint removal that has to be done in order to apply a good visual inspection.
Okay. I apologize, Dwayne. I think I maybe misstated the question. How do you inspect once it has been welded over paint?
Okay, so now we're welding over paint, and we're looking for quality problems. And actually, I think we're going to address that very next here, all right? So let's talk about what the quality problems are. And to the person who posed the question that Brent butchered, and
thanks, Dwayne.
You're welcome. If I don't address your question after this series and post it again, we'll try it again. All right, so what are the quality concerns of welding over these coated materials? I'd like to suggest that there are three big picture concerns. One is we need to make sure we obtain the necessary fusion. We may have extreme porosity, and of greatest concern, I think, to us as structural engineers is the possibility of cracking. So let's start with the issue of fusion. Now, this illustration is trying to show a piece of galvanized steel, and I've tried to use different colors to show that the virgin steel is underneath this coating of galvanized. And when I go to make a weld, it is possible on a very heavy galvanized part to fuse the weld metal to the galvanized, but for the weld to actually not fuse to the steel. Now, if that's the case, the strength of the connection is dependent on the strength of the galvanized coating. And that's not what you want to do for the design of your elements. That's not what we've assumed. So you have very little strength if you're not penetrating through the galvanized coating. Now, I'd like to suggest that's probably less of the problems, less frequently encountered problem. The more likely problem is that you will have extreme porosity in the weld. Now, when you heat the galvanized coating, it actually sublimates, where we go from a solid to a gas. If you've ever welded on galvanized material, there's a lot of fume that's generated, and that fume percolates through the weld. And if when it's going through the weld solidifies, you can end up with holes in your weld. Now, for structural applications, we do have acceptance limits for porosity. We're allowed to have some. We're not allowed to have a lot. And so that may be one of the problems you encounter. The other problem is that you may introduce into the liquid weld metal zinc. And if you do that, the zinc with a different melting temperature may segregate during solidification and cooling. It may also, it goes to grain boundaries, or it may go to the center line of the weld, and we could get into a crack. Now, cracks are the worst thing that we have when we try to make a weld. And so we need to preclude the cracking tendency in particular. Now, the American Welding Society has a publication that's now obsolete, D19.0. It was last updated in 1972. And I don't know if it'll ever be updated again, but in this publication is a list of factors that affect cracking tendencies on galvanized steel. And the factors include the silicon content in the weld metal, the degree of penetration of the weld beyond the root, the thickness of the base metal, which affects restraint, the coating thickness of the zinc, the microstructure of the zinc coating. And what I take from this list is there are a lot of things that affect cracking tendencies. Nobody said our job was going to be easy, but we have a lot of variables now that we have to deal with. So I want to be practical. I want to give you some good information because you have a job to do, and you have a structure that's going to be galvanized, and you need to weld on it, and you want to be certain that you're going to get the strength out of the connections you're looking for. So here are my suggestions for critical applications. Now you have to define what it means, what a critical application is. And that gets into redundancy, its loading on the structure, its consequence of failure. You define what's critical. But if you decide you have a critical application, the first item is I suggest that you qualify the welding procedure specification by test. Now, many of you know that there are pre-qualified welding procedures according to AWSD 1.1. Other welding procedures require qualification by test. In Design Guide 21, there's Chapter 7, and it discusses welding procedures. We're not going to get into that today. I would suggest that if you have a critical application that's coded, you not rely on pre-qualified welding procedures, but rather insist that the contractor run a procedure qualification test. Now, AWS has a Table 4.5, which has the title Limitation of Variables. The production welding need not be identical to the test conditions. As an example, if you run a test on 1-inch plate, well, should you be able to weld on 1-inch and 1/8-inch plate in the field? Well, that's probably within the limitation of variables. You run a test on a 1-inch plate, should you be able to go to 4-inch plate? Well, maybe that's too big of an expansion. That's the point behind Table 4.5. It defines those limits. However, bullet point 2, my words, Table 4.5 may not be adequate. That's really hard for the chairman of the D1.1 committee to say. I'm not speaking on behalf of the committee, but in my opinion, they're not adequate for some of these applications with coated materials. We need to be a little bit more restrictive. I say that because I've had experience where test welds were fine and too great a deviation from the test conditions were imposed or employed and resulted in problems on the actual project. So I recommend that you closely replicate the field conditions. Whatever you're doing in the field, mock it up, test it, see if you have any quality problems. I also suggest that you test the thickest coating condition that you're likely to encounter. Now, I think I have addressed the question of how you inspect the weld. If you are welding on these coated surfaces, use your standard inspection criteria. Most of these problems are going to show up as surface observable discontinuities. A fillet weld break test is a simple way to ensure integrity through the throat of the weld, and those are also outlined in AWS D1.1. Well, I'd like to move now on to our fourth topic, and that's welding on heavy shapes or on heavy sections. Now, some of you know about the project and the cracking that was experienced at the Orlando Civic Center in the late 70s. Now, these were not service loads. The truss, which was made with a cord, which was a very heavy jumbo section. Of course, the bottom cord is in tension. And for the convention center, it spans quite a length because you want column-free convention floor space. While this structure was being erected in the middle of the night, one of the cords fractured. And you can see the fracture of the flanges where this truss, the bottom cord was in the H orientation, if you will. Now, the second shot shows this in a little more detail, and the detail here is helpful to identify the contributing factors. Now, the first thing I'd like you to notice is that the weld itself did not fracture. This cracking is occurring in the base metal. Now, admittedly, it's a cracking that's welding related, But we need to make sure that we start by understanding that it was the base metal that was fracturing. Now here the same steel has been moved to the lab, and you can see evidence of what I just stated. There's the groove weld on one flange, the groove weld on the second flange, and the cracking in the flanges is removed from the weld. The web has cracked at this location on the left, but again, the weld is down below the web. What these cracks are associated with is the weld access hole region. Now, this is an example of what we used to call jumbo sections, or the heavy group 4 and 5 rolled shapes. ASTM has dropped the designation of the group numbers, and so now we just refer to these as heavy shapes. This W14 by 730 is going to be an example that we're going to use. It has a 5-inch flange, 3-inch web, 22-inch overall depth, and weighs 730 pounds per foot. And again, over the years, we've started to casually call these jumbo sections. Now, when we start welding on these heavier sections, what happens? Well, we start making larger welds. Larger welds have more shrinkage. The increased shrinkage means we're going to have more residual stress in these connections. Heavier sections also are more highly restrained. The higher restraint is going to create more triaxiality, and as we're going to see, the more triaxiality leads to less ductility. And finally, as I'm dealing with heavier shapes, the materials themselves change. There's less rolling associated with making the heavier shapes. They cool more slowly since we have thicker flanges and thicker webs, and that may lead to lower notch toughness. Now, notch toughness is typically measured with a Sharpie impact test. That's not the only way we can measure that toughness, but it is a measure of the resistance to brittle fracture when we have a pre-existing crack in an applied or residual tension field. So these are the things that make welding on heavy shapes more of a challenge. Now let's take a look at the cross-section of one of these shapes. The steel for the Orlando project, and that was 30 years ago or so, was ingot-based. Most of our steel today is going to be continuously cast steel. So some of these details are a little bit different from current steel production practices. When you poured an ingot, the low melting point constituents, including carbon-rich regions, would segregate toward the center. Now, when you went to roll out the shape, what was in the center of the ingot always stayed in the center. And as a result, in our cross-section down through the center, there would be a core region that typically had higher levels of carbon. Additionally, when the steel is rolled, the rolling action would break down these grains that would cause them to become finer or, become finer grains on the surface. The core region didn't require the same amount of rolling. And finally, these outside surfaces cooled more rapidly than this core region would. Now, for those reasons, and perhaps even others, there was a segregation that would take place. In shapes, we had reduced notch toughness in the steel. Now, this happens to be a segment of material taken out of Orlando. This is the thickness of the web. This is the flange. And you notice that the web to flange interface, when this steel has been polished and etched, we actually see the evidence of the steel showing up differently when we polish and etch the material. And this is that core region. If we go to the mill and watch these shapes being produced, we can see that the whole cross-section doesn't cool uniformly. Now, for the member on the left, and these are being rolled and coming out in the H configuration, if you will, you can see where the tip of the flange has cooled more, and you see a darker color associated with the tips of the flange. For the strand on the right, you can see the tips are cooled even further, but I'd like you to notice in particular the web to flange region, and even the color here is showing us that we have a little bit more heat at that center region. Now that has to do with the cooling rate that's experienced in that region. Now, for these reasons, and even perhaps more we haven't identified, when we get to heavier sections, we have a greater cracking tendency. And that's consistent with your experience, I suspect. When you're welding on heavier steel, you're more likely to see cracking than when you're welding on lighter weight material. Now, when we're talking about cracking, we are talking about a fracture problem, and fracture is controlled by fracture mechanics. Fracture mechanics primarily relates three variables: the fracture toughness of the material, the applied or residual stresses, and the presence of a crack, the orientation of the crack, and the size of the crack in the member. So we have three primary variables that we deal with to avoid fracture. Now, we want to optimize the toughness, and we want to minimize the stress and minimize the crack size in order to preclude fracture. So let's start by looking at fracture toughness, the things that happen negatively if we leave them alone with the jumbo sections, and what AISC has imposed to help to mitigate those kinds of concerns. Now, we already talked about this jumbo section in the cast core region. Now, if you were to order this steel back before Orlando, and if you asked for toughness, the specimen would be taken away from the tips of the flanges. This is simply because that's an easy way to extract the specimen. But if you test out in this region, notice you're not getting the properties of the core region. Now, these shapes have been successfully used for column applications for many years. This large cross-sectional area became very inviting to designers for tension members, specifically for trusses. So why is it we successfully welded this when it was in compression, but it became problematic in tension? Well, let's look at a tension splice. Now, in order to make a tension splice, I would normally cut weld access holes, and that allows me to place the backing in place. Of course, I have to bevel the flanges in order to receive the weld metal. Now, normally that kind of working is done with thermal cutting processes, and what I want you to see is that I'm thermally cutting on the flange area, some of the web to flange area, and even the cutting process is introducing residual stresses, and I'm working the steel, including the core region. Now, when I go to weld on it, I'm going to be welding into that core region as well. Let's contrast that with a typical column splice. Now, I realize that sometimes wind loads require complete joint penetration groove welds of column splices. Seismic concerns may do that as well. But there are many applications where we don't need to develop the full tensile capacity in a column splice. So we may have a detail, like I'm showing here, welded onto the surface of the steel of the web and then bolted as an erection aid in the field. Notice these welds would never be made on the core area of the shape. And then for the partial joint penetration groove welds, I would have a bevel, but that bevel may not go into the core region of the shape. So it's very conceivable, and in fact, experience showed that we could come up with compression welded connections on these jumbo shapes, and we had no problem. But when we came up with the detailing necessary for a tension joint, we started to see some of these cracking tendencies. Well, one of the things AISC imposed, and this is in the mid-'80s, these requirements started to come out, is now knowing about this low toughness core region, knowing that the ASTM location was on the tips of the flanges, AISC imposed a new requirement for these jumbo sections, and that was that the CVN specimen would be taken out of this worst case location, the center line of the shape, and T/4 into the flange. Now, of course, that's a more complicated area to extract steel from, but that became the required test. Eventually, that became a standard ASTM test. That's supplement 30, which is to the ASTM A6 specification. And out of that region, there was a requirement that the steel exhibit at least 20 foot-pounds at 70 degrees F. Now, that caused the steel producers to have to produce the steel differently in order to get the properties out of that location. And here is a new shot of the steel being made where they're artificially cooling that web-to-flange interface to ensure appropriate properties at that location. Now, the Orlando problem started out as shapes, but eventually the same provisions were applied to plate. And when the plate exceeded 2 inches, when you had a tension splice, we had the same requirement of 20 foot-pounds at 70 degrees. There needed not be a different location for that because that zone would be passed all the way through the plate. Eventually, filler metals were required to also have higher notch toughness. Remember, the Orlando case didn't involve cracking a weld metal. But once we start improving the system, increasing the toughness of the steel and other provisions that I'm going to discuss with you, then the same kind of magnitude of toughness, 20 foot-pounds at 40 degrees, was imposed on the weld metal. Now, that helped increase the fracture toughness. What can we do to mitigate or minimize stress? And we want to remember that this is the residual stresses of welding, not service loads, that drove this cracking. Well, here we have a CJP groove welded splice of one of these heavy sections. Now, of course, we provide the weld access hole that allows us to put backing underneath that top weld. It allows access for welding through the full width of that flange. But it turns out weld access holes do more than just that. I'd like you to think about the shrinkage that those groove welds make. This groove weld, the groove weld down below, will shrink transversely. It shrinks longitudinally. The web weld shrinks transversely. It shrinks longitudinally. Now, I want you to envision a cube of material right on the edge of a small weld access hole. So that's what we have here. Now, the yellow arrows here represent how the base metal responds. The residual tensile stresses in the weld are resisted by the base metal going into compression. But if I'm very close to the weld, I'm going to be in an area of residual tensile stresses. So let's look at this cube of material and examine the stresses on that material. Now, in the aqua color, I have the longitudinal shrinkage due to the groove welds. I have in yellow the transverse shrinkage due to those flange groove welds. And then in purple, I have the longitudinal shrinkage of the web weld. I have triaxial stresses applied to the steel adjacent to the weld access hole. Now, there's a wonderful little book that was written in 1941 by Dr. Max Gensamer. And Dr. Gensamer said this: "This is an important concept and needs to be emphasized. No shear stress, no plastic flow or deformation." Now, what Dr. Gensamer is telling us is in order to get plasticity, in order to get ductility out of our materials, we must have shear stresses present. And some of you may recall when you were taking a course in materials, it's along that 45-degree plane that we have the maximum shear stress, and the atoms of material move one with respect to each other along those 45-degree planes. Now, perhaps you, like I, learned about ductility with a standard tensile coupon. And you know that as you pull that member in tension, along those 45-degree planes, you get a maximum shear, and the materials start to slide along those 45-degree planes. They concentrate in a localized area, and we called that necking, didn't we? I think it's a little bit of a shame that engineers think about testing and coupons when we think about necking, but that's a subject for another discussion some other day. Nevertheless, we get this localized reduction that eventually ends up in fracture, and we get elongation out of our specimen. Now I'd like to go back to something you probably haven't dealt with since you were in school. Mohr circle of stress. And what I've drawn here is that uniaxial tensile coupon. Associated with this force, we get a stress, and we plot that as sigma 1. Now, there's another force involved in the system, and that is in the vertical direction. It happens to be 0, and so we're going to plot that up as the second stress field on Mohr's circle of stress. There's a third stress field. It also is 0, and that's stress in the direction of the screen. And of course, you learned that we draw a circle between sigma 1 and sigma 2. Associated with sigma 1, sigma 2 is a shear stress tau 1, 2. Now, we're going through this because we want to understand ductility. When we weld these jumbo sections, we want the weld shrinkage to cause yielding rather than fracture. And Gensamer says we need to have shear stress. Well, sure enough, we have shear stress in this particular application. Now, there's also a Mohr circle of sigma 1, sigma 3, and that creates shear stress 1, 3, tau 1, 3. And then there's a third Mohr circle of stress, and that's sigma 2, sigma 3. It shows up as a dot. There's a shear stress, tau 2, 3, associated with it. It happens to have a value of 0. So when I show you this plot, I hope you see 3 Mohr circles of stress. There's sigma 1, sigma 2, there's sigma 1, sigma 3, and then the dot is sigma 2, sigma 3. 3 Mohr circle of stresses. 2 shear stresses with a positive value, 1 shear stress with a value of 0. Now, if I increase sigma 1, my circle gets bigger. And my shear stresses start to increase on shear plane 1, 2, and 1, 3. Of course, 2, 3 doesn't change. It stays at a value of 0. If I increase my stress even further, I finally get out to what I call the yield strength of the material. Even though we commonly use that term, I think it's an unfortunate use of terms. Associated with that yield strength stress are shear stresses that exceed the critical shear strength in the material. Now, it's because these shear stresses exceed this critical shear strength that I finally get some deformation. And along the 45-degree planes, because I've exceeded the critical shear strength, these shear planes start to exhibit yielding. We call it yielding, but what's physically happening in the material is I exceeded the critical shear stress. Now, nothing happens on 2, 3 because it's still 0. Now, if I increase the load even, well, let's look at the shear planes first. Let's look at the shear planes of 1, 2. Here's the shear plane that's inside the material. Perpendicular to that, I have another shear plane. At a 90-degree orientation, I have shear plane 1, 3, and perpendicular to that, I have another shear plane. Now, those are the 4 sets of planes on which I start to get plastic deformation and flow. Now, let's increase our stress, sigma 1, even further. We're clearly into this area where we can now exhibit ductility. And if I increase my stress even further and I get out to the tensile strength capacity, then finally I start to get necking in this area. I'm getting a lot of deformation along these shear planes. I've experienced ductility. I increase load a little bit more, and bang, this thing breaks. I experience fracture. Now, this should be simply a reiteration of what you learned about Mohr's circle and what you learned in materials lab, and explains that tensile coupon we started with. Now we're going to complicate this a little bit. I'm going to add in a second stress field. So here's our cube that we looked at before. Sigma 1 is the same stress field we looked at before, but now I'm going to add in a second stress field, sigma 2, and I'm going to make it compression. Now, if it's compression, it's a negative value, so it shows up on the left-hand side of our chart. And we'll still have a sigma 3, but we're still going to make it 0. So now we have 3 stress fields, one with a positive value, one with a negative value, one with a value of 0. Now it's time to draw 3 more circles of stresses, and it's real easy to see all 3, isn't it? Now, associated with this plot, you see tau 1, 2, and even though I'm below the yield strength of the material, tau 1, 2 is pretty significant now. As a matter of fact, tau 1, 2 has exceeded the critical shear stress. So even though sigma 1 is less than the yield strength, I'm actually getting plastic deformation because shear plane 1, 2 has been increased by the presence of sigma 2. Now, if I increase sigma 1, of course, I have to increase the magnitude of sigma 2 in compression. Now I'm up to the yield strength of the material. My other shear planes are finally getting up to the critical shear stress. But 1, 2, look at what's been happening here. Lots of deformation before I even got to the yield strength. Now, if I increase that even further, now all 3 sets of shear planes are giving me plastic deformation. Eventually, I'm going to go out and I'll hit the tensile and I'll get fracture. Now, that's our second review of Mohr circle of stresses. Let's do it one more time. And this time, we're going to have 3 positive values of stress. There's sigma 1. Just to make it interesting, let's make sigma 2 tension of the same magnitude. And to keep it simple, we'll make sigma 3 tension of the same magnitude. So there's the plot of our 3 stress fields. Now we draw 3 more circles of stress. Do you see 3 circles? It happens to be a dot, but there's 3 dots there. There are 3 circles with a radius of 0. Now, associated with that stress field are 3 shear planes, and they actually have a magnitude of 0. Now, is any yielding going to take place at this point? We're at the yield strength of the material, but our shear stresses have not exceeded the critical value. So the answer is no. Let's increase it beyond the yield and go out to the tensile. Do you understand that when I have perfect triaxial stresses, I get fracture before I show any signs of deformation? So what's the takeaway? In order to get ductility, I need to get rid of at least one of these 3 stress fields, preferably more than one, because when I have uniaxial tensile, I have a lot of ductility. As a matter of fact, if I could add in compression, I could even get more ductility. All right, let's take theory and now apply it to practice. Remember, in Orlando, the cracking was occurring near the weld access hole regions, probably in areas where we had some workmanship defects. Now, here we have a beam-to-column connection, a very small weld access hole. Notice the access hole is terminating in an area of residual tension stress. Now I apply some service loads, and I have biaxial stresses. I have some shrinkage loads from a groove weld of the web. Now I have triaxial tensile stresses, and where I might have a workmanship defect, well, it's right in these triaxial stresses, and, well, I don't get any ductility out of those stress conditions. Now, what if I terminated that hole out here in an area of residual compressive stress? Surrounding the residual tensile stress is always a compressive stress. If I terminated this access hole in that region, now I'm adding in some compression, and when I put compression in the system, I had much more ductility. Now, around that workmanship defect, I'm more likely to get yielding to accommodate those shrinkage strains rather than fracture. Now, that's part of the logic that was imposed when the weld access hole sizes were increased back in the mid-'80s. You don't need an access hole this big for access for welding. These bigger access holes were to preclude the interaction of the residual stresses from the groove weld of the web and the groove weld of the flange. Now you see the dimensions here where the height, h, needs to be 1.5 T sub W, not less than a 1. 1 inch doesn't need to exceed 2. The width here is 1.5 T sub W, T sub W, of course, being the thickness of the web. So now let's apply those geometries to that W14 by 730, remembering that we have a 3-inch web. We have 4.5 inches off of the bevel. When you have 5-inch thick steel and you have a 45, I think there's a 30-degree included bevel, you have 2.9 inches. You add all that together, you have a 15-inch long weld access hole. Now that sounds huge, and it is quite large, but with 15 inches, there's no way that the residual stresses of the web weld interact with the residual stresses of the flange weld. In contrast, here's the weld access hole from Orlando. And you see it's been supplied. It's just big enough to get access for welding. That's it. Now, there's a few other things that we can do to minimize the stress. And one of the things we need to do is we need to recall that these are residual stresses from welding, and if I can reduce the volume of weld metal, I can help reduce the shrinkage stresses. So this is where we look into the detailing. Is a single V-groove weld or should a double V-groove weld be used? Well, the double V typically has less weld metal involved in the joint. That's going to be helpful to us. Another issue is to remember that the last weld pass is the one that has the most significant tensile residual stresses. So by controlling the placement of the weld pass, I can improve the situation. Now notice this weld has been made on the inside of the shape first. When it's flipped over and I start welding on the opposite side, the members with the highest residual tensile stress are going to be placed out away from the area where the weld access hole is. So now I put the very problematic high tensile stress welds out away from the problematic area where we're cutting through the core and making the weld access holes. I'll go as far as to suggest that maybe you're going to want to do a little overhead welding so that the last final stresses are out away from the region that we know to be somewhat problematic. Now the third thing on our circle was the crack size. And for fracture mechanics, the best thing we can do is make the crack size 0. Get rid of the crack. Now here's one of the weld access holes from Orlando, and you see some notches and some gouges in this region. When the access hole was checked with dye penetrant inspection, the pink is indicative that the dye is seeping out through the white developer, and so there are pre-existing defects in the weld access hole. That's why AISC now requires that we make the access holes differently. We preheat the steel to 150 degrees for thermal cutting. This is for the jumbo sections. After you cut the access hole, it's ground to bright metal. After you grind it to bright metal, you inspect it with dye penetrant inspection or with magnetic particle inspection. The goal is to start with crack-free surfaces. Now that has brought about an alternative practice that I like, and that is you use your drill line to create the hole that will constitute the outside radius of the weld access hole. Now this particular shot was taken before these weld access holes were made bigger. This would not comply, but it is a shot that shows you the drilling of the hole. Now after you drill the hole, it's a simple matter of extending that by flame cutting, removing that material, and now you don't need to grind the radius region. You can use your 9-inch grinder to grind these flats, and that's pretty easy to do. It was the radius region that was the problematic area. It was the radius where grinding was hard to perform. Now again, this is a very old shape, but you see nicely prepared weld access holes. You see nicely prepared bevels, and this has been prepared to receive the groove welds that it's going to have that we're going to have later on. I think we have a question.
Yes, Dwayne, we have a question with regards to thick base plates. Is laminar tearing still an issue with thick base plates when full, complete joint penetration welding to columns occurs?
The answer is yes, it still can be. I'm pleased to say that lamellar tearing problems in 2009 are much less as what we experienced through the 70s and the 80s. That in part is change in steel mill practice. But we still do have some lamellar tearing concerns, and large welds that strain the material in the through thickness direction are always problematic issues. Now, lamellar tearing seems to be most closely associated with welds right on the edge of the plate. And so for the example that's been cited, columns to base plates, usually we have some edge material that goes out beyond the edge of the material, of course, for your bolts and so forth, and should be less of a problem than, for example, in corner joints of fabricated boxes. All right, so I hope I addressed that issue. Here we're prepared now to do the welding, and as a bit of a case study to show that these jumbo sections can be successfully welded, this happens to be the EDS campus in Plano, Texas. You might recall that that was the company Ross Perot owned. It's changed hands several times since then. A signature building on their campus involves a suspended span, and the main entrance to campus actually is underneath that span. Here we have the Varendale truss with a superimposed catenary on the system. Now, this suspended member goes over a 164-foot span. It's a 3-story structure and indeed a 3-story truss. And you can see that there are some very heavy members that are in the system. There's not only compression members, but they have tension members because this does work as a truss. Now, when this building was built, some of these guidelines were still in, and today requirements were still in the very early developmental stages, and yet these concepts I've discussed with you were all considered. Now, here we see the layout of the truss in the shop. You can see sometimes there was a double catenary that straddled the columns in the system. The field connections were very carefully selected. The complicated connections were made back in the shop, and in the field we had simple butt splices. And this graphic or this photograph helps you see a bit of this concept. If you look at the node up here, you see that the connection, which will be the catenary to the column, that has already been made in the shop. And so in the field, we have a simpler butt splice where this stub is welded to the member that's going to be added in between. Now, this is obviously taken after construction has progressed, and you're starting to see both the catenary and the Varendale truss. In the center of the building, there is an open atrium area. We'll look at that a little bit later on. And there you see the catenary in that system. This is part of the double catenary. Again, the complicated connection was made up in here. I think this is a grinder, not a welder, but the field connection now is moved away from the column where the welder has better access, and we have a more simple type of weld to make under the field conditions. Now, here we see a little bit of the transition between the cords that have been added in the field and the shop welded connections, and then eventually this goes to a large weldment that was built up down here at the bottom of that catenary. And as we look back on the campus, you can see now the weld access holes, the relatively large size of the access holes, and of course those were left open after they served their function of helping the residual stresses to not interact one with the other. As we near completion, you can see through the glass the catenary is part of the architectural element, and indeed the atrium that we looked at before left the truss exposed, including the catenary that's been boarded in as part of the fireproofing system. Now, this is simply to illustrate that these materials can be successfully welded. We do need to go through all the proper techniques and make sure we employ those good practices. In a very closely related topic, we have welding under high restraint. And when we have high restraint, we need to increase the fracture resistance, reduce the shrinkage stresses, and reduce the restraint. Now, in Design Guide 21, Chapter 12, you'll find all of these items not only listed but amplified upon in the section of welding under high restraint. So I'm going to simply hit the highlights. We need to increase the fracture resistance. The most powerful way to increase the fracture resistance is to avoid cracks and notches. As soon as our crack size becomes 0, we don't have our fracture mechanics problem. Now, of course, we need to use materials with defined notch toughnesses. Higher preheats help us in that regard. Anything that we can do to reduce the shrinkage stress is helpful. I'm frustrating some of you by not reading this, but I'd like to suggest that your time should be spent reading the material in the design guide. We want to reduce shrinkage stresses, and you have a whole list of very practical ways to reduce those shrinkage stresses. We also need to reduce the restraint as much as we can. And again, at the risk of frustrating you, the design guide goes through these ways to reduce restraint and gives you a lot of practical ways to accomplish that purpose. Now we're going to move on to the second listing of 5 items and hopefully wrap this up in the next few minutes. Welding on HSS. Well, one of the things I'd like to point out quickly on HSS is unlike when we make connections, the connection design in HSS may affect the member size. So you select the member size as engineers, but when the connection is detailed, you may find the connection requires you change the member size. And that requires some interaction between the detailer and the designer when we get to HSS connections. Now, I'm not going to say anything more about that, just highlighting some of the issues we need to be concerned about. We also want to look at the overall configuration. Now, this is what's called a matched connection. And in a matched connection, the branch member has the same overall size as does the main member. Now, in many situations, it's not difficult to make that flare V or flare bevel groove weld in those situations. But what if your main member is heavier? Now, remember, the radius is going to determine, it's going to be affected by the thickness of the steel. And now we have a gap in the root. The welder's metal drips through the joint. Now, to preclude that, maybe you'd cut a special piece of backing. That's going to be more complicated. You could butter up the surfaces of that steel, grind it flush, and then bring in another member. Maybe you're going to go out and buy a special machine that will cut a special profile on the end of the shape so that you get a good joint detail. But there's another option, and that option's use what's called a stepped connection. And that's where the branch member is made slightly smaller than the main member. In doing so, it's simple to put a fillet weld all the way around the perimeter. It's not the only thing where we need to think about welding. Let's think about an overlapped connection. Now, many of you engineers prefer this because you know that as you go down through the center line of your member, if you put the working point in the center of your cord, you don't have any bending that you have to work with. That's normally very desirable, but I need to think about welding for a moment. How do you gain access to make all these welds in this overlap connection? Now, you might overlap it this way, but you can also see you're not tying in the flanges as you might want to do. That brings about the idea of a gapped connection that certainly is preferred from a welding point of view. It's a little easier to prepare the shape. And the gapped connection allows you to put a weld all the way around the perimeter very easily. It's easy to weld, it's easy to inspect. Now, of course, that means you're going to have to take bending loads through the cord. You're going to design that differently, and that may be a situation where the cord changes. Now, also, while we're talking about welding, we need to try to provide access for the welder to get to the joint. And that angle of a minimum of 30 degrees is recommended simply to allow the welder to gain access for making the weld, for allowing the inspector to gain access for getting the weld made. Now, while we're talking about HSS, I start thinking about cutting and preparing the material. And when we're dealing with box sections, it's very easy to make saw cuts to prepare the material. If we have trusses and we have diagonals coming in, very easy to make saw cuts on the box sections. When we have overlapped connections, we can make the various cuts that are required for that, but this is, again, an advantage of the gapped connection. You don't have to make but one cut. The overlapped connections are requiring multiple cuts, and every cut adds the opportunity to create some more fit-up problems in the field. Now that's for box HSS. Saws are easily used to prepare the material. When I go to round HSS, and in fact we even now have oval HSS, the joints are a little bit harder to prepare. Now I need to make these saddle cuts, which is going to require a more complex system. A common use of HSS is for architecturally exposed trusses. Now, when I'm using box HSS, I can start with an outside envelope of my member, if you will, and I can insert that diagonal member that transverse member very easily. I can drop the diagonals in place. It's fairly easily accomplished. I trust that you can see when I'm dealing with round HSS, it's impossible to drop that member in place. Now, I can configure this as a letter E, if you will, and then bring in the cord. That's one solution to the problem. A commonly used approach is to cut that transverse member, and you put in this little bit of a transition splice. Now I make the weld to the cord, but then I have to make this repair in between. It's one of the tools that can be used. My point is that if we welding people had our choice, we'd probably use box HSS. It's a little bit easier to prepare and fit. Now, I think we might have a question on box section or on HSS. Brent?
Yeah, this was in reference to one of the earlier slides. I believe it was where you had two square HSS members coming into each other. And the question is, can an HSS to HSS connection as shown, as I've described, be prepped for a true full penetration capacity versus a flare bevel / partial penetration capacity?
I'm trying to find the slide that might have been referenced here. And I think this may have been the one that was identified. And the question is, can we prepare it for a true CJP? And the answer is yes, we can do that. This is an example where that's been done. The previous examples we talked about could be the CJPs. I would suggest that using backing like this would be the more commonly used approach. I need to also tell you that my personal preference would not be using a CJP on the two flats that come together in a T configuration. That's an ideal place for a fillet weld, and you can develop the necessary tensile capacity by using a fillet weld at that location. Now I'm going to transition to AESS. And we'll start with some examples. Perhaps it was O'Hare Airport that we started to see the use of AESS in a more common application. Of course, if you start looking around, you see it in a variety of applications. It's a beautiful use of steel and certainly desirable in many kinds of architectural applications. Of course, my hometown is Cleveland, and our ballpark downtown, where our next to last place Indians competed this year, makes extensive use of AESS. Now, when we start talking about AESS, we're starting to talk about levels of pretty. And pretty and beauty is in the eyes of the beholder. So I'd like to suggest that mock-ups should be part of your plan when you're dealing with AESS. You're probably dealing with an architect, and what you think is beautiful may not meet the architect's expectations. Making a mock-up complete with painting with the final kind of paint can be very helpful in avoiding future communication problems. Now, the second point that I have, which I think is very, very helpful, when the architect is examining that mock-up specimen, it's appropriate to observe the specimen from the perspective of the observer in the actual building. That is, if the truss is going to be 30 feet up in the air, then the mock-up ought to be examined from a distance of 30 feet. Because what I could see from a distance of a foot, what I can see from a distance of 30 feet would be quite different. Now, there are a variety of notes that need to be communicated to the fabricator and to the inspector, and I'm going to be talking about those. There are also some technical issues that you need to be aware of when it comes to welding AESS. Now, here's an example where intermittent welds may be adequate for strength, but for AESS, the architect wants a continuous weld. Now, the continuous weld is going to cost more, and you're going to have more distortion, and I dare say it's probably lower cost for you to use caulk in between the welds than to weld it up. And if there's no reason for you to weld, maybe caulk makes sense. Now, here we have an example where the code doesn't allow us to weld on the corners. But if we have a painted structure, and particularly if it's painted white, we're going to get bleed out at that location, and we have a rusting problem. So for AESS applications, it may be desired to weld all the way to the corner. Now, we need to make sure when we do that, that we communicate to the inspector that this is the expectation. Otherwise, you're going to have a dispute. The inspector's going to say, no, you have to interrupt the welds at the corner. The concern is getting consistent quality in the corner, and that's another issue that may need to be addressed. We just talked about the importance of weld access holes. We made now a tension splice successfully, but maybe the AESS requirements say we don't want a weld access hole. Well, we can't get the groove welds in place without the access hole. So that's a non-starter, but maybe we're going to get somebody who is going to say, well, then we need to put a plug in here, and it's a little too easy just to weld the plug in place. Excuse me, it's easy to say weld the plug in place. Now we're adding more residual stresses into the region, right? And I don't think that's what you're going to want to do. Now, this is a location where maybe you bolt something in that area, maybe you use some mastic fill material and put it into those locations. What tolerance is acceptable, distortion is acceptable within D1.1 may not be acceptable for AESS. These are all things that need to be defined and communicated to those involved. Sometimes the welding processes need to be part of the AESS specification. Now, this was a shopping mall down in, or columns for a shopping mall down in the Carolinas, and the architect wanted a cast iron column look. And so you see the combination of some round tubes and angles that were welded in. They wanted no starts and stops in the weld. And submerged arc welding was used because it could be automated, has no starts and stops, no spatter, and made for an excellent appearance to these columns. Now, AISC has a document. You see the details of how to get that. Go to the website of AISC, AISC.org, and Google AESS or search AESS, and you'll find this document. Now, I know you can't read that today, but in this document you have a list of various variables that might be part of the AESS specification, as well as suggested applications where you might use these. It even supplies us with some estimated costs for the premiums associated with this, and this is a document that can be used with your architects as you work through those applications. Welding on existing structures. Now, when we weld on existing structures, we're dealing with historic steels. And it may involve steels that aren't made anymore. Again, for those of you who have Design Guide 21 on page 62, there's a review of various historic steels from the perspective of weldability. Now, some of you will also want to reference another design guide from AISC. I think it's Design Guide 15, that gives properties and the specifications of the steels over the years, written by Roger Brockenbrough. So that's another document that may be helpful, but Design Guide 21 takes on the issue of welding in particular. Now, this is a broad brush. Every estimate has, every rule of thumb has problems, but in general, if you're dealing with a structure that was built after World War II, in general, the weldability is pretty good. If it was built before World War II and it was welded then, the weldability is every bit as good today as it was back when it was built before World War II. The real challenge is on riveted structures. And if it was riveted, you don't know much about the weldability, particularly if it's an older structure. You get the steel analyzed. The design guide can give you some general trends, and you need to look into that weldability. Now, we also have the issue of welding on structures under load. And when we have structures under load, there's always a concern about loss of section properties under those configurations. And so here's the issue, of course. You have a weld. It's heated the steel. The steel has lost some section properties in the process, lost some yield strength in the process, and let's say we couldn't shore. Now what are we going to do? Well, maybe you can analyze this and assume the complete loss of the flange. Well, that's okay, but I suspect you'll find it doesn't work. And so if that's the case, maybe you're going to say, well, the whole length of the weld isn't hot, and maybe I just consider half of the flange gone. Well, once again, that makes sense, except that it probably won't work. So let's examine this heated region a little bit further. Some people over the years have said, don't put in transverse welds, put in longitudinal welds. Now, kind of at the root of the idea is we have less cross-sectional area that's affected by that. And of course, you know that surrounding the arc, immediately next to the arc, we have a very hot zone, but it doesn't take too long before it drops down on either side. Now, this is a plot of the properties of A36 steel as a function of temperature. And in general terms, by the time we get up to 1100 degrees, we have about half the yield and half the tensile. Here's a similar plot for 441 that we don't make anymore, but gives that same general trend as well. Now, here's what some other authors have said on the issue of welding under load. My mentor, Omer Blodgett, says the amount of material at temperatures greater than 650 F is negligible. Dr. Tide of West Janie Elstner, only a very small percentage of the cross-section experiences reduced properties. The late Dave Ricker, the impact of the weld orientation, whether it's longitudinal versus transverse, is typically inconsequential. And I say you need to check every situation. But these are some general trends that might be helpful to you. Now let's take Blodgett 650. And here you see the 650 degree, and you see you still have a substantial amount of strength at that load. For the 441, it's even a little bit higher. So maybe we don't lose quite as much as we're thinking of. Another concern is that of fire. And the issue of fire is not only the combustibles in the area, but also the work leads associated with the welding arc. Now, the welding arc is an electrical circuit, of course, and normally for new construction, the contractor just puts the work lead on the place near the steel, and the welding current finds its way out to the point of welding. That works okay on a bare steel frame, but if we're welding on an existing structure, we have electrical conduit, we have sheet metal ducting for the high vac system, we have gas lines that have natural gas in them, and any of these metallic systems could become the unintended work circuit. So I suggest that the work lead should be put as close to the source of the welding as we possibly can. Now, the next issue we have is that of welding on cold-worked material and strain aging. Many times we're dealing with structures that have been deformed due to service loads or natural forces. Overload conditions, hurricanes, maybe even seismic events, we could find ourselves welding on cold-worked material. Now, these bars represent the properties of hot-rolled steel. When we cold-work steel, we increase yield, tensile, but we decrease elongation and we decrease the notch toughness. Now, with that decrease in yield and tensile, we need to be concerned about the properties of the steel we're welding on. In addition to what the cold working is doing, we have this phenomenon called strain aging. And strain aging occurs when we heat steel between 400 and 700 degrees F. The yield and tensile further increase, the ductility and the notch toughness further decrease. So again, our hot rolled properties, our cold worked properties, and now the strain aged properties. And I'm concerned again about the loss of elongation and the notch toughness. Now, the amount of strain aging we experience depends on the chemistry of the material. Stress relief can help, but that's impractical. So what I'd like to suggest is that when we start welding on materials with that have been plastically deformed, we need to acknowledge that we have reduced notch toughness, and we need to make sure the material starts out notch and crack free. So when we have these cold worked areas, let's get those areas ground real nice and smooth. Because we have reduced ductility, we want to minimize the practices that increase the demand for ductility. And of course, we went through that under the provisions on welding on highly restrained material. Well, folks, we have gone past our limit, and I think I responded to a few more questions than we anticipated. So I think it's best that we wrap up our webinar, and we'll skip these last two topics of field welding and heat shrinking. Those are covered in the design guide, and I'd like to encourage you to look at those very closely, and that may be very helpful information that you can take advantage of, even though we didn't have the opportunity to explain that today. I hope those who aren't with us here in San Diego enjoyed the seminar. We look forward to your feedback. And with that, Brent, I turn it back to you, sir.
All right. Thank you very much, Dwayne.